Hello and welcome back to Multidimensional Integration. This is the video series where we talk about the different possibilities we have for integration in Rn. This means we look at volume integrals, surface integrals, and the different rules we can have there. Indeed, in today's part 10, we will look at an important formula we have in Rn, which is called Gauss's integral theorem or just divergence theorem. And this one can be used to derive a lot of other important formulas for the integration in n dimensions. However, as always, before we go into the details, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And please use the link in the description to download the additional material for the videos. And now I would say, let's immediately start by looking at the so-called divergence theorem in Rn. And this one requires that we look at an open and bounded set in Rn. This means this is a subset that has a well-defined n-dimensional volume. So maybe for the moment, let's call this open set capital Omega. And now I can already tell you that we actually have some more requirements because we want to look at the closure of this open set. So let's call this set M, and we see this is a compact set. So this is actually the full body we want to consider, and we want that it has a smooth boundary. We call this boundary del M, and the correct mathematical notion would be to say that this is a submanifold in Rn. I don't want to go into the details here, because I have a whole video series about manifolds, which you can watch if you are interested. We don't need to do that here, because I think the idea is quite clear. We have a full body that has a nice smooth surface area around it. Indeed, the pictures here are two-dimensional, but I think you should visualize most examples in R3. For example, you could say our omega is the open three-dimensional ball in R3. Then M is just the closed ball and the boundary is the sphere. And indeed, the sphere is a nice two-dimensional smooth surface in R3. Moreover, the smoothness implies that at each point on the sphere we can define a normal vector. And there I can already tell you, this normal vector is what we need in calculations. And with that we are ready for the divergence theorem in Rn. And you might already know, this one is also known as Gauss's integral theorem. And as already mentioned, if you want to see the proof of this theorem, please look at my manifold series. Here we don't need to be too abstract because we just work in Rn. So we have a compact set M that comes from an open set in Rn. And moreover, we also want to have a smooth boundary where you know this is just a generalized surface in Rn. This means we don't have any problem with the surface integral if you can write down a parameterization for del M. And there please don't forget, the parameterization does not have to cover the whole boundary, the whole surface. It's enough to cover almost everything to calculate the correct surface integral. And in fact, what we will integrate is a continuously differentiable vector field V from Rn into Rn. So at any point in the space Rn, we put an n-dimensional vector to it. And now such a vector field has a well-defined divergence at every point x in Rn. In fact, the divergence is easy to calculate, it's just adding up partial derivatives. More precisely, we have the sum that goes from 1 to our dimension n, and then we take the jth component of v, which is a scalar function, and then we take the partial derivative of it with respect to xj. So that's it. We take the components and the partial derivatives and add them up. Hence, this divergence is now a scalar function, which means it maps Rn into R. Therefore, we can just integrate it with a standard volume integral. This should not be a problem because we integrate a nice continuous function. And now Gauss's integral theorem tells us that this one is equal to a surface integral. We already know what a surface integral is, but here we have a special surface given, namely the boundary of our compact set M. And that's the thing here, instead of integrating over the whole set M, we just integrate over the boundary now. However, then instead of the divergence, we have the whole map V. But since it's not an ordinary scalar function, we have to use the standard inner product to make it to 1. And there, finally, the normal vector n from before comes into the game. We will talk more about this soon, but first you should see that we have our d sigma here to denote our surface integral. And on the other hand, you should note that these pointed brackets just denote the standard Euclidean inner product in Rn. And in fact, in important applications, this notation is not used, it's shortened to just a dot. Therefore, it's common to denote the divergence theorem in this short form as well. So please remember, this bullet just means that we have the standard inner product. And now, as promised, let's talk a little bit more about this normal vector n. In fact, we already know at each point at the boundary we have normal vectors, but we normalize them. So with respect to the standard norm, each vector here has norm 1. So we say we have a unit normal vector field n, but we also want that it is outward pointing. There you might already know what this means. You just have to look at the vector and follow it, and you will lie outside of our set M. So with the normal vector, we don't go inside M, we go away from it. And with these two additions, n is uniquely defined on the whole boundary. In the picture it's quite simple, it's just a unit vector that points outwards and is normal. However, now you know besides the unit normal vectors, we also have our vector field V. And there the formula with the inner product tells us that we only have to look at the component of V in the direction of n. In other words, we just have an orthogonal projection here. So only the perpendicular part of V through the surface area plays a role in the integral. And there I should note that a lot of people call this the flux of the vector field out of the closed surface. So at this point you realize that there are a lot of different names around this important divergence theorem. So for example, some people say flux integral for this special surface integral on the right hand side. Or in order to keep it simple, you can just say it's a special surface integral of a vector field. However, since the normal vector always goes in, some people shorten this integral notation even more. Namely, they just put the normal vector n into the surface element sigma itself. Hence, they write V in the inner product with the vector d sigma. Therefore, in that case, arrows above the letters are used to really make clear that we are dealing with vectors here. In mathematics, you usually don't see this notation here, but in applications that use the divergence theorem, you will definitely see that many times. In fact, it makes the whole formula quite short. The divergence over m is equal to this integral over del m. Okay, so now I think this is good enough for the explanation of the important integral theorem by Gauss, and if you want to see the proof, you can check out my manifold series. However, there you find an abstract proof, because you could also just do a concrete one just in Rn. But as you already know, in this series here, I want to look at the applications. So in the next videos, we will see what we can do with this divergence theorem. For example, you will see the integration by parts and Green's identities. So I really hope we meet again and have a nice day. Bye bye.